This lecture is the first in a series of three where we're going to be talking about strategies of data reduction. Datasets are often huge and they may contain thousands, hundreds of thousands, even millions of records. In one of the labs that we'll be working on, we're going to be looking at some Airbnb data that has over 100,000 cases in it. We need a way to summarize large datasets in order to get an understanding of the dataset, of what the dataset is telling us. We want to be able to look at summaries of individual variables. We want to look at the degree of variability in the dataset. And we want to be able to compare subgroups as well. We're going to start this effort by looking at frequency distributions, and along the way we'll also examine some related concepts of proportions and rates. So I'm sure you've seen a frequency table like this one before. It provides a breakdown of the religious preferences of Americans. It's pretty simple, but there are a few things to notice. First, it gives us the total number of people in the sample. In this case, this actually looks like data for the entire adult population in the United States. Second, it lists the different religions in order of their frequency. Protestants, the largest group, is the first on the list. Catholics, the second largest, is the second on the list, and so on. The none category is actually the third largest group, but it's listed last since, strictly speaking, none is not actually a religion. You'll also notice that there's an other category. It actually has more members than the Jewish category, but it's listed below the Jewish category because, again, other is not actually a religion. The same basic idea as the last table, but some of the other has been revealed. It's clear that there are more Protestants than Catholics, more Catholics than Jews, more Jews than Muslims, etc. But really, do you get a sense of the distribution of the various religions? You can more or less tell by looking at this table that there are about twice as many Protestants than Catholics, but that's about it. We need some way of measuring the relative number of people in each group relative to the total in the whole population. We need, in other words, to compute percents. And we have that right here. Although the number of Jews is rather large, 2,680,000, Jews, as this table shows, represent only a tiny fraction of the total adult U.S. population. How do we compute these percentages? A percentage is, of course, simply the number of cases, F, in the category of interest, divided by the total number of cases, N. For the Jews, we have 2,680,000 over N, which is in this case 216,367,000. It's worth noting here that I do not advocate multiplying the actual result of this division by 100 in order to express it as a percent, which is what many textbooks will have you do. You simply move the decimal point 2 places to the right and add a percent sign. You're not really multiplying anything when you convert a decimal value to a percent. You're just writing it out differently. So it's kind of silly to think that you're multiplying by 100 because that's just not what you're doing. All right. So frequency tables show a comparison between individual categories and the total. What if we want to compare two groups? For that, we need to compute a ratio. Here's the formula that we'd use. Consider the ratio of Catholics to Jews. As you can see, we divide the number of Jews by the number of Catholics, and this computes to 21.3. What this says is that there are 21.3 Catholics for every person of the Jewish faith. Or, put differently, there are 21.3 times more Catholics than Jews. By the way, I'd recommend that you put the larger number in the numerator, since that will give you a whole number result. These examples have so far been for variables that are measured on a nominal scale. What about variables that are measured on an ordinal scale? Well, here's an example of a frequency table that does just that, a frequency table for an ordinal variable. The only real difference here is that the categories are listed not from the largest to the smallest groups, but from the response that indicates more of the thing being measured, in this case, agreement with this statement, to less of that thing, again, less agreement. Other than that, there's not too much to worry about when we're looking at an ordinal versus a nominal measure. Things do get a bit more complicated when we want to create a frequency table for a variable measure, a variable which is measured on an interval ratio scale. Using the same approach that we took with nominal or ordinal variables, we might produce a frequency table that looks like this. To create this table, we're essentially treating each score as a category. We counted up the number of scores in each category, and as you can see, we have many scores where the frequency equals 1. Here there are 19 cases, and you can imagine what this would look like if we had more scores. It would be very long and just about impossible to interpret. What good, after all, is it to state that one student got a 77, one got a 78, one got an 81, etc.? You might as well just look at the raw data. If you look at the percent column, you also see another problem. It's clearly misleading to state that 5% of the students received an 81, since this only accounts for one single score. It really makes your table look as if you have more data than you actually do have. So when we're dealing with interval ratio data, we almost always want to place these scores into categories that make more sense. These categories are called class intervals. Here are two alternative presentations. The one on the left uses class intervals of 10 points. The one on the right uses class interval widths of 5 points. Which is the correct frequency table? I can't really give you any hard and fast rules, but I can give you some suggestions and a strategy to follow. First, notice that the class intervals begin with a multiple of 5. The first rule of thumb, then, is to have your class intervals begin with a number that people are comfortable counting by. In most cases, this would be a 2 or a 5. You may recall that the lowest score in the data set was a 58, but if you started at 58 and created class intervals of width 5, you'd have 58, 62, 66, etc. Most people can't visualize intervals like that, whereas we're all familiar with counting off by 2s or counting by 5s, or of course 10s, which are a multiple of 5s, or 20s or whatever. So rates are another way of summarizing data. We use them when we want to make a comparison. Here are 3 examples. That slash character means per. So we have thefts per vehicle owned, children per family, guns per person, etc. Let's take a closer look. There are about 270 million guns in circulation in the U.S. today. The U.S. population is about 327 million people. So we might say that there are 0.825 guns per person. The thing is here that people reading a figure like this may have trouble understanding this notion of a fractional gun, about an 8/10 of a gun. What does that actually mean? For this reason, what we typically do is we get rid of the decimal and write this out like this. There are 83 guns for every 100 Americans. And of course, 83, we've just rounded that 0.825 up a bit. By the way, this is worth pointing out that this is probably a low estimate. Other sources report over 120 guns per person. And by comparison, there are only about 5 guns per 100 population in England. Some good news. New York State has the lowest rate of gun ownership of all 50 states and the District of Columbia. All right, let's move on to the final topic I want to cover in this video, which is data visualization. Data visualization is a huge field, and if we have some time later in the semester, I may devote an entire class to it. Let's briefly cover some basics, though. The text covers pie charts, bar charts, histograms, line graphs, and time series charts. Let's take a look. Of course, here we have the ubiquitous pie chart. Pie charts provide a graphic representation of the data in a frequency table. We've talked about using frequency tables for nominal, ordinal, and interval data, though frankly, I've never seen a pie chart that uses anything other than nominal data. If you have data that has some element of quantity associated with it, there are probably better choices. The thing is, one of the problems with pie charts relates to the fact that it isn't really possible to show more than just a few categories. In this pie chart, for instance, it's impossible to discern the relative proportion of any groups except for Protestants and Catholics, and the none category, and then again, none isn't even a religion. So there are a couple of workarounds. Here's one example. Even here there are some challenges though. First, again, this non-religion of none dominates. It's the third largest category. Second, without the inclusion of the percent amounts, it's really not possible to get a sense of the relative number of Jews, Muslims, Buddhists, and Unitarians. If you need to provide numeric percentages at the same time, why not just simply use a table? If I had my way, basically I would ban pie charts, except maybe if you have 3 nominal categories, none of which are so small that it's hard to tell what's going on unless you put a number in there. Here we have a table that's a little bit better at showing these amounts, a bar chart, again showing the same data. Again, it is difficult to figure out by looking graphically at these very small categories: Jews, Muslims, Buddhists, Unitarians, etc. If you've got to put an actual number in, why not just go with a table? This is kind of an interesting chart. It shows 2 things at once. This shows the change in homicide victimization rates over time, and at the same time, the gender differences in those victimization rates. We would call this an information-rich illustration. Another information-rich chart. This is from some work I did a while ago that examined satisfaction with individual clinics at an agency providing housing services to mentally ill adults. There were 5 clinics, A through E, and residents were asked to respond to a series of questions that asked about their satisfaction with the services they received in 3 areas: staff, the advice they received, and the facility in which they resided. The emphasis here is on the components of satisfaction. Overall, it looks like residents are pretty satisfied with the staff, but less satisfied or not so satisfied with the facilities. My color choices here aren't the greatest because these 2 purples are hard to tell apart. The purple that in this case indicate Clinic B and Clinic E. This chart enables managers to see their individual site's strengths and weaknesses. Clinic C, for example, is doing very well with satisfaction with staff, but needs to improve its facility. Clinic E is weak overall, but improvements in its facility are probably the problem to tackle first. Maybe they could ask, maybe the folks in Clinic E could ask their colleagues over at Clinic D for some help with facility related issues, because they are scoring the highest for satisfaction with the facility. Again, the same data, but in this chart we look at the overall level of satisfaction with each facility and each of the component parts of that satisfaction. The staff at Program E were pretty worried when they got a look at this chart, because clearly they're the worst performing clinic in the group of 5. All these charts, by the way, were created with Microsoft Excel, and creating them was really very easy. We'll be talking about some of the newer charts Microsoft has built into Excel in upcoming labs. This is a histogram, and a histogram is a special type of bar chart that has its own characteristics. The horizontal or x-axis contains the bins. These are simply the class intervals. Because of the way I curve the scores on my exams, they're always expressed as decimals. The labels are a bit misleading because of the way that Excel computes frequencies We'll get into that in more detail when we actually work through this in a lab. But the last bar, for example, contains the scores that are greater than 0.9. The bar just to the left of that bar contains scores that are between 0.8 but less than 0.9. Of course, the vertical or y-axis shows the number of scores in each bin. It's worth observing here that in a histogram, the bars touch. This is a convention, but when you look at this type of a chart, you know immediately that it's a histogram. And you use histograms by and large to look at interval ratio data. You wouldn't use that with ordinal. You wouldn't really use it with, you certainly wouldn't use it with nominal data. We will be spending a good deal of time with histograms a little later in the semester, since their shape is very, very important to the types of statistical procedures that we will be covering in the class. This chart looks at a time series data. In this case, changes in the marriage and divorce rates between 1950 and it looks to me like 2010. That really should be labeled, but the source where I took this from just didn't bother to label it. Note that the vertical axis shows marriage and divorce rates per 100,000 population. These rates are computed just as we described before. If we didn't show them per 100,000 population, we'd have something like a rate of 0.0004, 0.0006, etc. So this just makes more sense than thinking about fractional people. Well, that's pretty much it. I hope that you'll agree that these concepts are not too difficult to understand, and you can practice with them by looking at the homework assignment for this week.